Okay, we're going to continue working through examples on a past exam. This is question 5. Find the interval of convergence. Interval of convergence is I of C of the power series Okay. Solution. So it's very similar to what we did before, right? So this is our power series. We take x to be fixed. I'm going to let ax be these terms. Minus 1 to the k, x minus 3 to the k over k. We take the absolute value of ak plus 1 over ak. Using the ratio test, the minus 1s will just disappear. We're going to have x minus 3, we will have k over k plus 1, and that's it, right? So the limit, as k goes to infinity, ak plus 1 over ak. As before, the x minus 3 doesn't depend on k, we pull it out from the limit. And that is just equal to x minus 3. And we need this to be less than 1, okay, in order for the thing to converge. Okay. So, or maybe I should put that as a sentence. Okay. So converges absolutely. If x minus 3 is less than 1. So the radius of convergence is 1. Let's draw a picture. So the power series is centered around 3. Okay. And so x minus 3 to 1 is going to take us from 4 to 2. Right? So anything which is strictly between 2 and 4 will be such that this power series converges. But now we're looking for the interval of convergence. So the interval of convergence is a set of points, whereas the radius convergence is just a number. Okay, they're different things. We need to find the radius convergence first to find the interval convergence. Right? So the radius of convergence is this R here, where if we consider where the series is centered around, call that number A, then it will converge absolutely between a minus r and a plus r, right? So think of a as being the center and r as being the radius. So a ball of radius r on the real line is just a minus r to a plus r. That's why this word radius comes in here, okay? So r, the radius convergence is 1, we see from this. And the interval convergence, well, we have to figure it out. It's a set of all the points for which this series converges. Well, it definitely converges if we're strictly between 2 and 4, but we need to check out what's going to happen at the endpoints. So, check the endpoints. If we put in x equals 2, what happens? Then we're going to have minus 1 to the k, minus 1 to the k, so that's just going to be positive. So our series is just going to become this, which diverges. And if x is equal to 4, then we're just going to have the series, the sum from k equals 1 to infinity, minus 1 to the k over k, which by alternating series test, this thing definitely does converge, so converges. Cool. So, interval of convergence, which is the set of all the points which it actually converges, is going to include 4, but it will not include 2. So it's going to be like this, 2 to 4. Right? Anything which is strictly outside The closed interval 2 to 4 definitely will not converge, because then this ratio will be strictly bigger than 1. So this is the entire set of points for which this power series converges, and this is the answer. And that is option C. All right. I should have said this already. This is 2003, midterm 3. From the University of Cincinnati, Calculus 2. Okay, let's do another question. It's question 6. So, f of x is represented by this power series, the sum from n equals 1 to infinity x to the 2n plus 1 over 2n factorial. What is the value okay. So, solution. What's going on here? Well, this is a question trying to make sure that you understand what a Maclaurin series is, right? So, if this guy is represented by this power series, then we have the representation of a function with this Maclaurin series has an explicit formula, which is given by this. Or I should say explicit general formula. We found this out just by taking the derivative of this series and plugging in the value x equals 0. We found out that the coefficients in front of the x, the n, have to be of this form. This was an easy thing to check. So it's equal to this, and it's also equal to this expression here. Oops. Okay, so remember when we talked about power series and I said where a power series converges, it is just as good as a polynomial, right? So any good thing which is true for a polynomial is going to be true for power series wherever it converges. So we can use that in this case. So let me put this aside. So if we had, for example, ax squared plus bx plus c was equal to, say, 3x squared plus 5x plus 2, and that was true for all x, you guys would know straight away that this implies that a equals 3, b equals 5, and then c is equal to 2. There's no other way this can be true, right? Just differentiate this guy, or we can just plug in x equals 0. There's lots of different ways we can see why this has to be the case, right? So when we have a power series, it's the same deal, right? So this guy is equating these two power series, and the only way they can possibly agree is if the coefficients in front of them all agree, right? So in this case, we have this coefficient right here agrees with this coefficient agrees with this, and this coefficient agrees with this, right? So if we write out the first few terms of this power series right here, what we're going to have in the general form, we're going to have f of 0 plus f prime of 0 x plus f double prime of 0 x squared 2 factorial, and then so on. And that thing has to equal this thing. So let's write out the first few terms. So when n is equal to 1, we're going to have x to the 3 over 2. When n is equal to 2, we're going to have x to the 5 over 4 factorial. When n is equal to 3, we're going to have x to the 7 over 6 factorial, and so on. Okay? Now, the only way this power series can equal this power series is by exactly the same principle if all the coefficients agree. So in particular, the x to the 5 term, which is, say, somewhere here, has to equal to the x to the 5 term right here. Okay? So, what does that mean? That means that the fifth derivative at 0 over 5 factorial has to be the same as 1 over 4 factorial. Yeah? Which, I'm running out of space. Which in particular means that the fifth derivative at 0 has to equal to 5 factorial over 4 factorial. 5 factorial is 5 times 4 factorial, so this is just equal to 5. That answers our question, right? So what's it testing? It's testing that you know the general formula for the Maclaurin series, and it's testing you know this basic principle that if we have two power series and they agree, that's only possible if the coefficients all agree in exactly the same way as we know for polynomials. Keep in your mind the basic principle that, once again, power series, wherever it converges, is just as good as a polynomial. Anything you can do for a polynomial, you can do for a power series. It will also be true. Cool. Let's do another question. Oh, I should say which option this is. This is option C. So this is option C. Okay, question 7. Find the exact value. Okay, so the hint here is in the wording find the exact value. This is a particular explicit series, and you might remember at the beginning when we learned about series, I said there's only two kinds of series where we can explicitly calculate. There are geometric series and there are telescoping series. All the other ones we don't know exactly what the answer is, what exactly the series sums to. Except after this section on Maclaurin series. Because after we did this section on Maclaurin series, Taylor series, we had some explicit Maclaurin series for various well-known functions. And if we simply plugged in the value into that well-known function, then that would give us another series that we could tell the exact value of. Right? And this is what this guy is. It is absolutely not a geometric series. This 2n factorial kills that possibility, right? It is also not a telescoping series. We don't have any kind of n minus n plus 1 structure. So it's got to be a well-known Maclaurin series. Maclaurin series is a well-known function. We plug in some value into it, right? And for this, you're going to just have to know some basic Maclaurin series. There are not that many. There are about 6 you have to know. And the best way to know them is to just work them out a few times. if you look at this for a bit, what should come to mind is that this is the Maclaurin series of cosine. So solution cosine of x, this guy we did work out, it's k equals 0. I think we're doing n here. N equals 0 to infinity minus 1 to the n, x to the 2n over 2n factorial, right? And if we just plug in pi into this, we get exactly our series, right? So cosine of pi, let's call this thing star, is equal to star, right? And what is cosine of pi? We have the picture of cosine in our head. Cosine of pi is minus 1. So that's it. Very quick, very easy if you know what this question is getting at. And you should know what this question is getting at because of the particular wording, find the exact value of. So these kind of questions kind of giveaways if you have this in mind. So keep this in mind. Be ready for some question of the kind, find the exact value of. Right? There's only 3 possible things. Geometric series, telescoping series, or you're plugging in a value into a Maclaurin series of a well-known function. Okay. Next question. Question 8. Let's change pens. Compute the limit as x goes to 0 of x to the 6 minus 3 x to the 7 over cosine x to the 3 minus 1. Okay. Solution. This question is again using your knowledge of Maclaurin series. Okay, so what you're going to have to think of is that, okay, cosine of x to the 3 is actually a power series. If it was a polynomial, then it would be the kind of question that you've had many times before when you have some kind of rational function and then you've taken the limit as x tends to 0. It isn't quite this because cosine is not obviously a polynomial, but it's a power series, which is a lot like a polynomial, right? So we have the formula for cosine up here. We actually can just write down what this thing is, right? We're just going to put x to the 3 inside this formula. Sum k equals 0 to infinity minus 1 to the k, x to the power 3, and then 2, so it's going to be 6, and then over 2k factorial, right? Cool. So let's write out the first few terms of this. So when k equals 0, we have this. We should be consistent. This is k, not n. I want to make that neater. So let's write out the first few terms. When k equals 0, 0 to the fact 0 to minus 1 to the 0 is just 1, x to the 0 is 1, 0 factorial is 1, so the first term is 1. When k equals 1, we have minus x to the power 6 over 2 factorial, so x to the 6 over 2. And then when k equals 2, we're going to have plus, and then we're going to have x to the 12. And then we're going to have 4 factorial right here. And then we're going to have a bunch of other terms. Right? The next one will be k equals 3, so it's a minus. We're going to have 18. And then we're going to have 2 times 3 factorial, so 6 factorial. And then other terms like this. But we don't care too much about the other terms because when x goes to 0, then only the leading order terms are important, just like you're very familiar with taking these limits for rational functions, right? So if we consider this expression, so the limit as x tends to 0, x to the 6 minus 3 x to the 7 over cosine x to the 3 minus 1. This is the same as the limit as x tends to 0. x to the 6 minus 3x to the 7. And then what do we have? Well, the 1s are going to cancel, so we're going to have minus x to the 6 over 2 plus x to the 12 over 4 factorial, and then a bunch of other things. Oops, this is minus x to the 18 over 6 factorial. But notice all of these things to the right of this are all going to be powers of 6, right? Or they're all going to be higher powers of x to the 6, right? So from this point onwards, all of these guys are going to be incredibly small compared to actually this expression right here. Yeah. So as x tends to 0, we can care less and less about everything to the right of all of these guys. We could factor out, we can actually factor out an x to the 12 from all of the stuff on the right hand side. So 1 minus x to the 6 over 2 plus x to the 12, and then we're going to have 1 over 4 factorial minus x to the 6 over 6 factorial, and then a bunch of other terms like this, right, which go off to infinity. So all of this stuff here will just be a series that converges. So this is just something which is just some function in front of x to the 6, so when, sorry, x to the 12. So when x tends very small, this whole thing right here is just going to vanish. We can just forget about it. Okay? So this is really a lot like 1 minus x to the 6 over 2 for very small x. Okay. So the error between this guy and this guy is of order x to the 12, which is very much smaller than x to the 6, right? So we can just care about the leading order terms. We can factor out x to the 6 from the top and the bottom, right? And if we do that, then what happens, then we're just going to see that this limit will just be minus 1. It'll be 1 over minus a half, which is just minus 2. Yeah? Okay. That is option D. Okay, let's see if we can squeeze the next question in. Probably not. All right, let's see if we got a smaller question we can do. No. All right, let's just erase the board then. Well, we can at least write the question, right? So let's write the next question. So question 9. Find the C3 coefficient in, oops, oh yeah, this is okay. Okay, so what's this? This is the binomial expansion, or the generalized binomial expansion of this expression 1 minus x. Okay, so this is one of the slightly more technical topics we discussed. And it's asking us to find the third coefficient of this thing. So right at the first two terms, we're going to have c1 plus c2x squared plus, oops, this is wrong, it's c0 plus c1 plus x plus c2x squared plus c3x to the 3. So we deduce the general formula, but I do not want you to memorize formulae. That's completely the wrong thing to do. So we're not going to do that. We are just going to work it out. We're just going to work it out, and it won't be difficult. Let's do it. So we have the third root of this. And then we want to find what C3 is. Okay, so we know that CK is just the kth derivative at 0 over k factorial. This is the Maclaurin series. This is the general formula. We're very happy with it. So we're just going to have to differentiate our function. So this is f of x is equal to the third root of 1 minus x. We're just going to have to differentiate it a number of times to find out this coefficient. Differentiate the first time. We can differentiate functions to some power. That's not hard, right? So it's 1 over 3, 1 minus x to the minus 2 over 3. Differentiate the inner function, we have minus 1. Differentiate it again. We're going to have 1 over 3 times minus 2 over 3. 1 minus x to the minus 5 over 3. Differentiate the inner function is now minus 1 times minus 1 is plus 1. Differentiate the third time. 1 over 3 minus 2 over 3 minus 5 over 3. 1 minus x to the minus 7 over 3. Differentiate the in thing, we now get a minus 1. Okay, so we have minus, 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 so it's going to be minus overall. So it's going to be minus 10 over 27. 1 minus x to the minus 7 over 3. We're doing the max series, we're applying this at 0, so the third derivative at 0 is equal just to minus 10 over 27. Okay, we know that C3, just from this general formula, is the third derivative at 0. I'll keep writing the third derivative in a different way, but you know what I'm doing. Over 3 factorial. 3 factorial is just 6. So what is this? This is minus 10, 27 times 6. So that's the same as minus 5 over 27 times 3. What's 27 times 3? So times 2 is 54. Add again. 54 plus 27. It's like 81, right? So 4 plus 27 is 31. So yeah, it's 81. So it's 81. All right. Let's see what the answer is. We'll see what the multiple choice is. So that is option A. Cool. Let's do another one. Now we're going to do the free response. Let's change colors. This is question 10. Determine if the series converges absolutely or conditionally or diverges. Okay. Solution. Okay, what I want you to first observe here is that this thing n to the 3 over e to the n is a sequence of terms that's going to 0 incredibly fast. This e to the n is absolutely killing the n to the 3, right? Because the exponential function, as we've learned many times, is way, way, way faster growing than any polynomial. So this is going to 0 incredibly fast. Yeah? So there is indeed a very good chance that this thing is converging absolutely. The only time it converges conditionally on the terms don't go to zero fast enough, right? When we have an alternating series, we just need the terms to go to zero at any rate at all. That's still going to converge. But if we put the absolute value signs around, then we need the terms to go to zero fast enough. Again, the key example is 1 over n. The sum of 1 over n does not go to zero fast enough. That thing diverges, but if we have 1 over n to the p for any p bigger than 1, that is fast enough, right? So the issue of something converging conditionally is just when it doesn't go to zero fast enough. This guy looks like he's going to zero really, really fast. It looks like it's going to converge absolutely. So let's guess that that's the case. If we think it's converging absolutely, then there's a number of tests we can do. A very natural test would be to use the ratio test because we see this e to the n structure. So e to the n structure is sort of giving you the feeling that in its bones, this thing is like a geometric series. It looks like a geometric series, probably a geometric series morally like 1 over e to the n, right? And that being the case, then we'll know it converges absolutely. And that's what the ratio test is going to detect. It's this X-ray machine where you can apply it to some ugly series like this, and you'll see if underneath the unimportant details, in its bones, this series is like a geometric series. In this case, our guess is the geometric series 1 over e to the n. So let's check it out. So let's do an is minus 1 to the n to the 3 e to the n. If we take the absolute value, and what happens? The minus 1s we don't care about. What we're going to have on the top, we're going to have n plus 1 to the 3 over n to the 3, and just going to have 1 over e, right? Which is the same as n plus 1 over n to the 3, 1 over e. And if we take the limit of this thing, and then goes to infinity, it's 1 over an. I've done this a few times. You can pull out this 1 over e, and it's just the limit of this thing over n to the 3. And if this is a free response, maybe you'd want to put more details. You want to factor out the n from the top and bottom. Let's maybe do that. So that's 1 over e. This is the limit as n goes to infinity. So what's this? This is 1 over n. This is plus over this thing. So the 3. Something to the 3 is a continuous function. We can pass the limit inside, and the limit of this, this is a 1, of course. The limit of this is just 1, so this is just 1 over e. E is like 2.7 something something, so this is indeed less than 1, so converges absolutely by the ratio test. Cool. And the fact that an plus 1 over an basically has the ratio of 1 over e does indeed say that a to the n is morally like 1 over e to the n, because 1 over e to the n does have this power that the ratio of an plus 1 over an is 1 over e. So underneath the unimportant structure, this guy is like this guy, and therefore, well, when we take the absolute value of this guy, it is like this guy, and therefore it will converge absolutely. So this is, again, what I think is quite a straightforward question. Cool. All right, so keep doing past exams, do the practice problems, and this coming exam should be a straightforward one for you all.